Hey guys, just thought to make a quick simple video on a magnetic field pattern around straight wire. Okay, let's say first I've got a, what do I have here? I got a cardboard with a conducting wire poked through it, and I run a current through it. What's going to happen? If I were to put my plotting compass, what you see is that first you see, there's a magnetic field formed. Couple of things to take note of magnetic field. Magnetic field basically consists of, okay, concentric circles as you can see here, okay. And next thing you also notice, when they're closer to the wire, the fields are actually stronger. And how you tell it's stronger? Because the concentric circles are actually closer to each other, right? Okay, so as the distance move further away from the wire, the field actually gets weaker because you can see the concentric circles actually gets further away. Okay, and one more thing, there's a direction, right? So in this case, the direction of the magnetic field is actually in an anti-clockwise direction. Okay, how are you going to tell that? Basically, you use this thing called the right-hand grip rule. There are two main things in the right-hand grip rule. You got the thumb and you got the rounded fingers, right? So the thumb will actually represent the direction of the current, and where your fingers turn, that will actually see and represent the direction of the field. So in this case, you can see my fingers are actually going in an anti-clockwise direction. Okay, so next thing, let's say I extend this wire, okay, and then I poke it. After poking it up, I poke it down here, okay. So you can see if I use the Fleming's right hand grip rule, you actually get a anti-clockwise direction of magnetic field on this wire closer to me, and this one further up, because the current is actually going the opposite direction, is actually going, the magnetic field will actually go in a clockwise direction, right? Okay, so just zooming in on this part, if I were to look from the top, what do I actually see? Okay, what I see here, you can see the magnetic field, just like I mentioned, is going in the anti-clockwise direction. And this for point one. The point two, over here, it is the magnetic field is going in an anti-clockwise direction. Okay, just now that was clockwise, and this is right now anti-clockwise. Okay, do you notice something here? Oh, what's this? This is a cross and a dot. Okay, this is basically just tells you the direction of current. What you can do here is that imagine this to be an arrow. If you are standing behind the arrow, what do you see? The arrow is going away from you. You basically just see the feathers behind the arrow, which is basically a, yes, that's right, it's basically a cross. And if you're standing in front of the arrow and you're looking at the arrow that's coming to you, whoa, what do you see? You see the tip of the arrow, right? It happens to be just, that's right, a dot. Okay, so if I were to extend this coil and I just keep doing it, keep running it up, what do I get? I get a solenoid. You can see over here, the magnetic field is actually going out from the left and in from the right, correct? So if I have this, can you guess what pole is the one on the left? That's right. The one on the left is actually north, the one on the right is south, because magnetic field lines, remember, we always draw from north to the south end, right? Okay, so we can predict the magnetic field of the solenoid again using the right hand grip rule. Okay, how do we do that? Okay, so basically your thumb, in this case the fingers actually represent the current in the coil. So as long as the current in the solenoid is actually going, you can see it actually wraps around. Can you see it actually goes around it, so goes behind and in front and behind and in front. So that's why your fingers also go behind and front. It follows the direction of the current. Okay, so if you stick out your thumb, the direction of your thumb always points to the north pole. Okay, all right, just one last thing. And why do we study all this? Okay, so we got this final setup here. You can see we got a horseshoe, which is basically a permanent magnet, and we got a wire. And if I were to run electric current flowing through the wire, what do you see? You see two magnetic fields, right? First, the magnetic field is produced by the permanent horseshoe magnet, which is a straight magnetic field from north to south, basically. And if I were to run a current through a wire, I get, that's right, I get a circular magnetic field. And combining these two in 3, 2, 1, boom, check it out. Okay, what do we see here? Okay, we see how do these two magnetic fields actually interact with each other. Okay, to explain further, this is actually what happens. You can see a circular and a magnetic field. This circular magnetic field is from the wire, and this straight magnetic field is from the magnet. If you were to interact both of them, get ready for this. What do you see? Boom! You actually see on the left the magnetic field lines are all in the same direction going up, so it will still go up. But on the right, some are going down and some are going up. So what will happen? You see less magnetic field here, right? So basically, there is a it seems like a catapult motion. There's a catapult motion towards the right. Okay, what is this? This is basically none other than the motor effect. Okay, so if you were to strip any motor, for example, a fan or an air conditioner, anything that moves as moving parts, you will notice inside not just do they actually have a wire with current flowing through, they will actually have strong permanent magnets. So basically, strong permanent magnets with a wire flowing through, you get two magnetic fields and you combine that together, boom, you get this force. Okay, so that brings us to the last part, which is the force. How do we tell the direction of the force? Okay, other than drawing this one, which will be quite a chore in the quite difficult for you to do this, come up with this every time. Fleming came out with the left-hand rule way of telling which is the direction of the force. Okay, for example, if I've got this model here, you can see inside the wire here, not sure you can see, but if it travels from plus all the way to minus, um, since the current inside this magnetic field is going outwards, that means towards outside of of this paper, going outside or slightly to the left from where you see if it's going in this direction. Okay, what's gonna happen? Okay, you use Fleming's left hand rule. You can see the magnetic current, which is represented by the index finger, essentially pointing down, and the current is actually just now we mentioned going to the left, right? Correct? It's going out of the slide. So since it's going out, you point that and your thumb naturally will point to the right. So that's why the force is to the right. Okay. Conversely, if I were to swap the current around, okay, this time it travels the current going in. You can see my middle finger representing the current now goes in the opposite direction, and my index finger still pointing down. This will result in a force from my thumb actually pointing it into the horseshoe magnet. Okay, so just to quick recap on Fleming's left hand rule. Fleming's left hand rule, if you have got a permanent magnet and a current flowing through a wire that goes in between these permanent magnets, you create what we call a force. You can tell the direction of force by using Fleming's left hand rule. To help you remember, force in the thumb actually stands for father, followed by index finger, mother, and child being the middle finger. So father, mother, child representing force, magnetic field, and child. All right, hope you enjoyed this video. I will see you guys soon.